this a little bit, right? So just a reminder, right? If we've got an array and we've got this 3, 6, let's see, 9 and 7, right? The way merge sort works is there's two parts. So there's the merge sort one, which is going to continue to split this until we have sorted arrays, right? So this is more of like, hey, if array.length is less than or equal to 1, then we know it's sorted. So we can go ahead and, return our array. Otherwise, we have to split this. So how can we split an array? Who can help me with that? How do we split an array?
Go with the middle index.
What, David?
I said go find the middle index and split it in half.
Yeah, exactly, right? So David says we got to find this middle index. So we can do that by getting like our length. So we'll say like let mid, and this is just going to be our array length divided by 2, right? Obviously we have to floor that as well. And then we can just slice to get our left and to get our right. So we've got this left, which is just our array dot slice of 0 to mid. And we have our right, which can just be our array dot slice from the mid, right? So now we've isolated our lefts and our rights. So we're able to split this array. So we have these two different arrays. Keep going. So once we've got our left and our right, we can think of this as creating another array here. And we have our other array of 9 and 7 here. So kind of think of this. So then we have to keep splitting these. So same process where we get our 3 and we get our 6 and we get our 9 in an array and we get our 7. Right? And so now is when it gets hit with the merge. So what we want to merge is only sorted arrays. So first, we're going to merge these two arrays, and then we're going to merge these two arrays. So this ends up going into this world of 3, 6, and this one of 9, 7. 7, 9, I'm sorry, that's not merging correctly. 7, 9, right? Because it needs to stay sorted. That's the whole point. And then on the recursive call, these are going to get merged because these are both now sorted arrays. So we're going to end up with our 3, 6, 7, and 9. So we get this overall pattern, right? That's how it visually looks. How it spreads out into small pieces and then it comes back together. And so let's actually remind ourselves of how the code looks. So, screen share here. And so when we are working on this, that's weird, it's not really taking up the full screen. There it is. Right, we've got those two methods. So we've got this merge method that's taking in those two sort arrays. And it's saying, hey, while each one's got a length, let's just compare the first element in each array. And the reason we can do that is because they're both sorted. So we can really use that to our advantage. And so whichever one is smaller, we can just shift it off of that array and push it into our output. So eventually one of these will become empty and our output will be full, and as well, it will be sorted. So we're going to put this in a new array. We're going to destructure our output because this is our sorted array. And then we're going to destructure array 1 and array 2. Now, one of these is going to be empty. Otherwise, we wouldn't have broken out of the while loop. But we don't care which one is empty, and we don't know which one is empty. So, I mean, we could say, hey, if array 1 has length, then we can go ahead and merge that. Else, if array 2 has length, we can merge that. But with working with arrays and destructuring, we can just do that as well. And it's no harm, no foul by destructuring an empty array. It's just going to turn into nothing. So it's okay. And then so our merge sort works similar, right? If our array's length is less than or equal to 1, we know this array is a sorted array. So we can just return it. We've taken our mid index. We've got our left side and our right side. And then we're going to keep calling our merge sort until we get sorted arrays. So we're going to call merge sort on left. We're going to call merge sort on right. And then at the very end, we just want to merge them back together. So this is a sorted array, and this is a sorted array. So our merge will handle that perfectly. Okay, so that's our merge sort review. Any questions on that?
I have a question.
Yeah.
Just to be clear, in order to use the merge sorts, the arrays have to be sorted, right?
In order to use the merge part of merge sort,
Yeah.
yes. Those definitely need to be sorted.
For both of them or just for the first merge?
Both of these have to be sorted for this to work.
Okay, got it. All right.
Otherwise, we have no guarantee. But then we'd have to look at more than just the 0th index.
Got it.
Yeah. Good question. Any other question here? Okay. Cool. So let's test our knowledge on sorts. So let's go ahead and answer this poll, this little quizzy poll. Let's see how we do.
Hey, Corey.
Yes.
I think that I might be a host.
Oh, yeah?
I was wondering why.
Yeah, somehow you became a host.
My poll's looking funny.
Can you see the poll now, Danny?
Yeah, I can see it now.
Okay. Huh, wonder how that happened. Oh, I did it instead of John by accident. So let's just take another minute. All right, cool. Let's end the poll. Let's share these results. Let's go over this together. So, the time complexity of bubble sort. We got 55% of people. Everyone can see the poll, right?
Yeah.
Yes?
Yeah.
Okay, great. Thank you. We got 55 people say that it is n squared, that it is quadratic. That is correct, right? That is the bubble sort time complexity. If we remind ourselves when we share the screen, the way bubble sort works, right? We have got this nested loops that are going to keep going potentially for every element. It's going to loop through every element. I mean, there is a best case scenario when it was n squared, but the average case, which is the one we're really looking for, is in fact n squared. So good job, 55. The other percent, right? That's not correct. N is linear. It is impossible at this point in time to sort something at linear speed, because that would mean that you had to make no comparisons of any elements with any elements. Log n is the fastest time there, right? That's like a binary search where we'd be just cutting the data in half. If you could sort something in log n, you'd win a Nobel Prize. N log n is the best sorting that we can do. But we'll see those answers later. But bubble sort is a n squared. Gotta know these ones. They could come up. The time complexity of quicksort. Cool. So 75% of people on this one say n log n. That is correct, right? Quicksort does have a worst case scenario where we could talk about it being n squared especially if we knew where the pivot would be and someone put in like a pathological input where they like purposefully made it a crappy time, but we can mitigate that risk by grabbing a random pivot point with each movement. So great job for that. The next one we've got is time complexity of insertion sort. This is n squared. 40% of us got it right. Insertion sort, if we remember, is we are going through it and we're looking, hey, we're assuming the very beginning of this sort is sorted, and we look at the next element and see if this is part of that sort. So is this greater than our number before? If it's not, you could think of it as pulled out, and the other numbers become shifted over as it continues to check and find where it should be inserted in the beginning of the array. Okay, let's take a look at time complexity of merge sort. 60% of people said n log n. That is correct. Merge sort is guaranteed to be n log n time, because even if it's sorted in any way, it's always going to split all the way apart into the sorted where we have sorted arrays at a base level of length of 1 or less, and then it's going to get put back together. So it's always n log n. Let's keep going. Quicksort. Quicksort and merge sort must be implemented recursively. 60% of people said false. That is correct, right? There is no function on the planet that has to be implemented recursively. Anything in the world that is implemented recursively can be implemented iteratively. That is just a rule. Some are significantly more complicated to implement if you're not using recursion. But every single thing can be created iteratively. Can somebody tell me a negative to recursion? What's a negative aspect to recursion? Okay, somebody's writing in the chat. Let's see. So Nober says time complexity. Not really. I mean, it does take maybe a little bit of time to make that stack frame, but there's something else that's even that I want us to think about even more. Like, what about if I was taking the factorial of 50 or 100, 500,000? What would happen?
It has to continue running until it reaches the base case.
Right. So what? That's right. So Doug says it's going to continue running until it hits that base case. But why is that a bad thing with recursion?
Can't break out of it.
Can't break out of it. No. Let's try it. Let's demonstrate this point with the actual code. All right, so let's write a basic factorial recursively. So let me just comment this out for now. And we'll say const factorial. Factorial, it takes in n. And our base case, I think, is if n is less than or equal to 1, let's just go ahead and return 1. Otherwise, we will return factorial n minus 1. times n. Okay, and we will go ahead and console log factorial of, I think this will work, 100,000. Okay, let's go ahead and see what happens. Oh, maximum call stack size exceeded. Is there something wrong with the code? Let's
Isn't
try.
there- oh.
What?
I don't think there's anything wrong with the code, but
No.
because the code was like, because you put 1,000. I mean, was that 10,
100,000.
100,000? The it's doing a lot of what you call the calls.
Recursive calls.
Yeah, it's doing a lot of recursive calls. So maybe it's reading it like, oh, maybe it's too many calls, so we exceeded that. So it's probably reading it as if the code is incomplete, but it's not.
Absolutely. You're totally right, Henry. Right? This is trying for each recursive call, it creates a new stack frame. We only have so many stack frames available to us. So we cannot do that. Well, if I had written this iteratively, right? Const fact takes in n, and we just say like that output is equal to n, 1, sorry. Oh yeah, sure, I don't know how to do this. And then I'll just do while n is greater than 1. We'll just say output times equal 1, I guess. And then we'll, oops, times equal n, my mistake. N minus minus, and like, let's just return output. Right, so if we call it here, if we call fact here, where we're running iteratively, right, we're not going to time out. It gives us a huge number. It says it's infinity, but it doesn't overflow. All of these numbers are humongous, and we definitely have 100 stack frames. But the point is that if things only worked recursively, there'd be some really negative outcomes, right? Because of stack overflow, because we can only make so many stacks in a recursive call. I think it's something like 9,000 or something. Does anyone remember off the top of their head? No? Okay. But there's some number. It varies from machine to machine. But our sorting algorithms, most likely under the hood, all are running iteratively. So that way they don't have to worry about how large of an array comes in. Otherwise, merge sort, quicksort would be crap if we could only make them recursive. It's an easier implementation. You typically don't need to make them iterative unless you're making dsort for JavaScript that everyone will use. Okay, so let's keep going. Bubble sort finds the smallest elements first. 55% of people said false. That is correct, right? Bubble sort is looking for the largest elements first, building to the end of the array. Insertion sort builds from the front of the array. 75% of people said true. That is correct. Nice job. Quicksort, when visualized, looks like a tree with an unsorted array as the, should say root, I'm sorry, and a sorted array as the leaves. 70% of people said true. That is correct, right? It looks like kind of like that. And our merge sort is the most reliable sort in terms of time complexity. 75% of people said true, and that is also correct because we are guaranteed n log n every time.
Basically the same. It doesn't have much.
Okay, Isaiah, thank you. All right, so I will stop the share here, and I just want us to see these. There's a pretty good visualization tool right here. So we have our numbers here, and this is bubble sort. So let's just watch bubble sort one more time and see how it's working. 40, it's going to keep taking the largest number and moving it until it reaches the end. And then it's going to start from the beginning and do that again. Right, so 38 it's gonna get moved all the way to 44, but then 44 is gonna start moving. And then 46, 47, those are sorted. Speed this up a little bit. Right, and this just is gonna keep going all the way until the end. This is our bubble sort. It's bubbling up, the biggest numbers first, then we're sorted. Let's take a look at insertion sort. Sort. Right, so this is, it's taking it, it's assuming these on the left here are already sorted, and it's moving pieces, looking for its spot, and sliding everything over. Slow it down just a touch. Right, it's not there, it's not there, it's not there. Finally, it's bigger, it's gonna slide in.
So Corey,
Yes,
for insertion sort, so it takes an element, it's looking at an element, and it's comparing the left and the right side to see if it's bigger or smaller.
it's only looking at the left. It's assuming that the left side is sorted, starting with the element 1. So element 1 is guaranteed to be sorted because it's thinking of it as only an array of length 1.
Okay.
And then it's checking, then it keeps moving and it says, hey, is this item actually bigger than the one on the left? And if it's not, you can think of it as being taken out and then having the number shift over until it actually is bigger than the number before.
Okay.
Yeah, thank you, Deja, for sending that link. Okay, let's take a look at merge sort, how this works. Right. This visualization of merge sort is a little bit confusing. Oh, there, I see it's been split and now it's sorting these arrays. Yeah, this one is confusing, but it is how it's happening.
Oh, I think it did the left side first and then the right
Yeah.
side, and then it's going to merge the both sides
So
together.
that's right. And it always will do the left side first if you call merge sort on the left side first, because it has to keep going down those recursive calls. Okay, and let's see how this sucker does quicksort. It's gonna see, it's choosing things that are less than or greater than the pivot, putting the pivot in the middle. So now it's going from the front of the array. So everything in green is on the left side, everything on purple is on the right side. Okay, it's got its pivot there. And those are all the sorts. Okay, so watch those when you need a reminder. It should be helpful. Later today, after lunch, we are going to talk about trees. But until then, I want you all to work on what you need to work on, but also to watch these videos by the time we get back from lunch. So I found these are a couple more Hasib Qureshi videos, and he's going to introduce trees for us, and then I will touch on it. But I would like everybody to watch these videos first so that they can come in with questions and be ready to hear it again. Okay. So this is required watching. It will take about an hour. If you have a video speed player, it'll probably take you about 40, 45 minutes.